Hello, my name is Darcy Kenworthy. I'm a postdoc at the Oscar Klein Center in Stockholm, Sweden at Stockholm University. This work is entitled 2 out of 3 Ain't Bad, a two-rung SH0ES distance ladder. This work was performed with my advisor in my PhD, Adam Rees, as well as the entire SH0ES collaboration. So the SH0ES collaboration was founded in 2005 to use a 3-rung distance ladder to measure the Hubble constant to better than 1 kilometer per second per megaparsec. This 3-rung distance ladder is based on geometric distances to nearby Cepheids, such as Milky Way parallaxes. These absolute distances allow us to calibrate the 0 point of the Cepheid period luminosity relation, the Leavitt law. We then go out into the local universe at less than 40 megaparsecs, or redshifts of less than about 0.01, to find nearby galaxies which have hosted type 1a supernovae. These galaxies are targeted for follow-up, and we measure Cepheids in these galaxies, allowing us to transfer the absolute calibration from the geometric parallax to type 1a supernovae. We then use the type 1a supernovae to measure the Hubble flow at redshifts greater than 0.023, where the random motions of nearby galaxies, peculiar velocities, are small compared to the Hubble flow. This allows us to get a precise measurement of the Hubble constant using well-understood standard candles. This program has been conducted over the past 20 years, and in our most recent release in 2022, we had 42 Cepheid calibrator galaxies, 3 geometric anchor distances, as well as about 200 type 1a supernovae in the nearby Hubble flow. This measurement found that the Hubble constant was 73.2 plus or minus 1 kilometer per second per megaparsec. Recent work by UK Murakami, a graduate student at Hopkins, improves this to 73.3 plus or minus 0.9 kilometers per second per megaparsec. So the topic of SH0ES inevitably leads to the Hubble tension, the disagreement between the SH0ES measurement of the Hubble constant in the late universe and the prediction for the Hubble constant based on measurements of the early universe by the Planck satellite. This disagreement is now at about 5 sigma. And there are many other measurements that have been conducted based on early or late universe techniques. And generally, we have found that late universe indicators give a larger Hubble constant than early universe indicators. So this is very interesting. Could be a sign of new physics, but it's necessary that we check every rung of our distance ladder to ensure that we're not being contaminated by some kind of unknown systematic. So type 1a supernovae are wonderful, but we need to check them as well. So one way to do that would be to entirely eliminate them from the distance ladder. If we find that cutting them out of the distance ladder doesn't affect our result, that would be an indicator that type 1a supernovae are not the source of the Hubble tension. So what we want to do then is a 2-rung distance ladder using geometry and SH0ES Cepheids to measure the Hubble constant independently of type 1a supernovae. As I said earlier, though, the reason that we are using these type 1a supernovae in the first place is to get out into the Hubble flow where peculiar velocities are a smaller effect. For nearby supernovae with Hubble redshifts of 3,000 kilometers per second, peculiar velocity error of 250 kilometers per second is going to be a lot more significant. The median redshift of our sample, in fact, is 0.006, which means that peculiar velocities are about 20% of our signal. You can see that there's a lot of scatter in this Hubble diagram showing Cepheid distances against redshift, and it's going to be very difficult to disentangle the predicted SH0ES and Planck values of H0 based on this data alone. Further, because peculiar velocities are ultimately sourced by gravity, which is sourced by mass, which is large-scale structure, these peculiar velocities are correlated across the sky. And the size of the Cepheid sample here is about 40 megaparsecs. The BAO scale is 140 megaparsecs. So our data is very correlated indeed. Now, it's possible that there could be voids at much larger scales than we could ever really constrain with the Cepheid data. If there were a local underdensity of about 30%, then that would inflate the SH0ES value of the Hubble constant by about 5%. So this could be something significant. But looking at the type 1a supernova data, we don't see any indication that there are large underdensities on scales too large for us to constrain. In fact, we find that we can constrain this to about 0.7% based on the supernova 1a data alone. So anyway, we don't want to use that, however. So what we use are peculiar velocity reconstructions. These are reconstructions of the nearby universe based on galaxy redshift surveys that use number counts of galaxies across the sky as a function of redshift and sky position that go from the distribution of redshifts to the underlying distribution of mass. And the two reconstructions that we use here are Karakadal 2015 and Lilo and Nusser 2021. These reconstructions show excellent performance on reducing scatter in distance indicators, but there are uncertainties that remain even after using them to correct our data. And there could be correlations between the corrected redshifts in different parts of the sky that might be unclear to us. In order to account for this, we looked at the power spectra of these reconstructions. We found that there are, if we compare these reconstructions to the power spectrum of lambda CDM, we find that they are a very good fit for lambda CDM with Gaussian smoothing, which is expected. These reconstructions use Gaussian smoothing in their process. So things on scales of 1 megaparsec are, those features are much too small to be constrained by really any reconstruction algorithm you can imagine, unless you've solved n-body gravity fully and have infinite data. So we basically find that there is physics that these reconstructions can model, and there's physics that they can't model. And we take this as one of our uncertainties in our peculiar velocity corrections. We also include an additional term shown here in red, which includes the differences between the two reconstructions that we have. We take the differences of these and add the power spectrum of that difference to the power spectrum that is unmodeled. And we use this power spectrum in red to compute the expected covariance between the Cepheid galaxies in our sample. And we can remove all of this stuff that's crosshatched out of our uncertainty budget. This makes an enormous difference in the precision of our final measurement. When we compare the lambda CDM covariance for the pairwise covariance of objects in our sample. So each point on this plot is a pair of Cepheid galaxies where we've calculated the expected covariance between them as a function of their separation in 3 dimensions. The lambda CDM covariance shows a very high amplitude of more than 300 kilometers per second per megaparsec. And this data is correlated at enormous scales that mean that we would have very significant correlations in our data. When we use our uncertainty budget based on the differences of the reconstructions, as well as the unmodeled physics that's present, we find that we've reduced the amplitude by a factor of 2, but much more significantly, we've reduced the scale of the correlations by an enormous factor, which means that our final data is much better constrained. And we find that ultimately the Cepheid data prefers this reduced covariance. It prefers these corrections at more than 3 sigma significance. So we're confident that we've correctly budgeted for our peculiar velocity uncertainties. We also included other systematics, not just peculiar velocities. We included a bunch of different Cepheid systematics. The baseline SH0ES analysis treats these as variants, where they're after the analysis is done, it's reanalyzed with a different technique, and ultimately that difference is propagated into the SH0ES error budget. Here we added these uncertainties directly into our covariance matrix. This shows the Cepheid covariance matrix used by the baseline SH0ES analysis. And this much more complicated covariance matrix shows the covariance matrix we use for our analysis here. The systematics that we've accounted for here include the metallicity of the Cepheids, the reddening correction for the Cepheids based on host galaxy dust, different treatments of the Leavitt law, as well as different treatments of outliers. We also accounted for selection effects in our sample. So galaxies have a co-moving density. As a result, the distribution of galaxies with distance goes as the square of the distance due to volumetric effects. This scaling implies a distance-dependent bias in redshifts that goes as about 1 over the distance squared. We see this tail in the Pantheon data analysis, where the low end of this redshift range, there's this 1 over distance squared tail. Here we simulated this effect and ultimately accounted for it in our final analysis. However, our selection function was somewhat uncertain. SH0ES did not ever have guaranteed time. It was accomplished over 20 years through year-to-year Hubble Space Telescope proposals. So there were a couple of possibilities for how this was done. Ultimately, we accounted for 2 kind of limiting scenarios. One was that SH0ES used type 1a supernova magnitudes to target nearby galaxies. One was that SH0ES used redshifts to target nearby galaxies to ensure that these galaxies were within the Hubble Space Telescope's ability to measure accurately. In order to do our analysis jointly, considering all the effects I've talked about, we use a hierarchical Bayesian model that can marginalize over the uncertainties of these peculiar velocity reconstructions, the correlations of our sample, the unique distance redshift relations created on each line of sight by the different peculiar velocity profiles, as well as the selection of the SH0ES sample. So we take this uncorrected Hubble diagram over here, where there's no clear way to differentiate what the Hubble constant actually is. And we use our corrected model to make this Hubble diagram instead. And we have a much cleaner set of data with a much more precise measurement of the Hubble constant. So again, this is showing our residuals. So we take the observed distances in red, which have the redshift subtracted out of them. In gray, I've shown the scale of expected uncertainty from lambda CDM. We correct these distances with our model. And these are our final residuals, which show very good properties, chi-squared close to 1, reduced chi-squared close to 1, no apparent trends with redshift, and generally much less noisy than the previous data. When we compare the Cepheid and supernova distances, we find that the 2 agree very precisely. The type 1a supernova and Cepheids have a chi-squared of about 50 between them, with about 72 degrees of freedom. So in our final result, we evaluated 12 different treatments of selection, as well as different modeling choices to evaluate the associated systematics. We found that without using galaxy reconstructions, we could constrain the Hubble constant to 71.6 plus or minus 4.5. When we include the information from the galaxy reconstructions, which are highly preferred by the data, we find our fiducial result of 72.8 plus 2.4 minus 2.2 kilometers per second per megaparsec at 2.4 sigma discrepancy with Planck. So our conclusion then is type 1a supernova systematics are not likely to be the source of the Hubble tension. Thank you very much for your time.